Thank you all for coming and thank you for inviting me. So yeah, today I want to define to you what Segal categories are and give you a feel of why they are weakly enriched categories. Obviously, I also need to show you what weakly enriched categories are. At the end, I'm going to talk about my research project, and that's joint with Wendy Lowen and Arno Mertens. And I think we have plenty of time and some definitions that are more technical. I'm going to give them more through examples. So if you're not still super set on how something is working, you can ask me and I can make more drawings or give more examples. So, okay. I start by reviewing what plain category is. So in the category C, we have a collection of objects, and we usually represent them by points, and then we put the name under it, so X, Y, Z, and so on. Maybe a warning, that first object is called X, not U. It's just my handwriting. And then for every pair of objects, X and Y, we have a set of homes from X to Y. I call them usually arrows because we draw them as arrows. So directed lines that go from X to Y. And then we have a composition function. So given any triple of objects, X, Y, and Z, we can take a pair of composable arrows, so from X to Y and to Y to Z, and we can compose them. But for the purpose of this talk, I want you to think that composition not only gives you this arrow, but also gives you this triangle. So secretly, you take two composable maps and you get a triangle that it is the composition. Then we require that this composition is associative and unital. The unital part for this talk, we are not going to focus on it too much, but if you're really interested at any point, you can ask me what role the unitality is playing or not. But again, for the associativity, for the purpose of today, I want you to think of it as a tetrahedra. And how so why does that make sense? So why is associativity a tetrahedron? So you see this left face is the composition F after G after F. This right face is the composition H after G. And so that makes the bottom face be this right-hand side, so H and then G after F. And the back face is H after G after F. And the fact that there is a unique arrow that goes from X to W means that this edge is shared by both. And so these two compositions must be the same. Okay? So yeah, the point of this slide is, well, to recall what the category is for those not so familiar, but also to make you notice that the data can be neatly organized into labeled points, lines between labeled points, triangles with labeled points, tetrahedra with labeled points, and then we will make this a theme. But first, we are going to enrich categories. So I'm not going to define what a general enriched category is, but they are meant to describe the situation that you have when the set of arrows from one object to another is a bit more than a set, or maybe even something else. But so in top categories, so a category enriched in topological spaces or a topological category, these are all synonymous, we have a collection of objects still, but now between any pair of objects, we have a space, a topological space of arrows. Then for each triple, we have a composition function that now we require it to be continuous. So it's the natural choice of map between a topological space and a topological space. And then again, we ask that composition is associative and unital. So it's basically a category, but in the set of arrows, we have a topology. So for example, the category of smooth manifolds with smooth maps between them is a topological category because we can put a topology, the compact open topology, for example, in the set of maps from one manifold to another manifold. Okay, but this is an algebra colloquium, so R is a ring. And we have also categories enriched in chain complexes, or also called DG categories. Again, they have a collection of objects. Now, between any two objects, there is a chain complex of morphisms. Yeah, and then the composition map is a chain map, so the natural notion of function between chain complexes. But also notice here that we no longer have the Cartesian product. We have the tensor products. I mean, we could define them with the Cartesian product, but when people say chain enriched, they mean with the tensor product because the most abundant examples have the tensor product there. Again, composition is associative and unital, just in the same way. And for example, an example of a category which can be enriched in chain complexes is the category of chain complexes themselves. So we know that there is a mapping complex between any two chain complexes. Yeah, okay. So now I want to take the next step and go to weakly enriched categories. But for that, I will need to give an alternative definition of enriched categories. And that alternative definition is going to have as a basis this idea of the points, the lines, the triangles, the tetrahedra, and so on. So let me start by introducing this category, delta O. So O is a set, which you should think of as some set of objects. And now what are the objects in the category delta O? They are non-empty tuples of elements in O. So let me give some examples. We have the tuple just with the point, with the element x0, and we represent this object by a point labeled x0. Similarly, we have the pair x0, x1. We draw it, or we represent it, or we can think of it as a line that goes from x0 to x1. And then we also have a triple, x0, x1, x2, that we think of as a triangle. And then we also have the tuple x0, x1, x2, and x3. We think of it as a directed tetrahedra with the label, with the vertices labeled like that. And then, of course, maybe we also have x1, x2, x0, x1, x2, x3, x4. That's going to be a four-dimensional tetrahedra, and so on and so on. But okay, how do why do I tell you that these like sequences of elements have this geometric shape? Well, that comes from the maps that there are between these objects. So here is a definition, but this is very opaque. Please don't be scared and don't try to understand it like right now. I am going to give you a feel for these maps in a slightly different context. So we consider functors from the category delta O up into top. Okay, so what is this? For each object in delta O, we are going to have a topological space. And then the arrows in delta O will like be mapped into continuous functions between these spaces. But okay, nothing better than an example. Okay, so we have the objects xy in delta O. So we have a corresponding topological space big X of xy. And I ask you to think of the points in this space as lines that go from X to Y. Lines in where or lines of what? for now, that's really abstract. Like I will give examples afterwards, but just lines. So they have a starting point, which is given by the map D1, and they have an ending point, which is given by the map D0. Moreover, if you have a point X, you can also obtain a sort of degenerate line that never leaves the point X. So the fact that you have these maps D1 and D0 that give you the start and the finish, and the fact that you have this map S0 that takes a point and gives you something that never leaves this point, let's say, really gives you the feel that things here should be thought of as lines. Then we move on up a dimension. So what are the points in this space big X of X, Y, Z? So they are triangles. And the map D2, for example, gives you the edge that goes from X to Y. So it really goes from the triangles to the lines with according labeling. Of course, we also have a map that gives you this bottom line. You also have a map that gives you this one, but I'm not going to show you. And then, for example, a point in this topological space should be some sort of tetrahedra. And again, you have the maps that give you the corresponding faces. So D, you can maybe think of as delete. And then 1, or this number that you can see here, tells you which vertex to delete. So, for example, in this case, we start counting at 0. Yeah. So in this case, D1, you delete the vertex in the position 1. So that's Y. It's like you delete Y. What do you get? You just get this line. Similarly, in the first one, for example, delete 1, you also delete Y. So you just get, you cannot have a line that ends nowhere. So you just get the vertex. Again, for example, 0, 1. Ah, this is wrong. D3. Yeah, this map should be called D2, actually, because we are deleting the second vertex to get the backface. So apologies for that.
Should land in X, Y,
And should land in X, Y, W. That's right. Yeah, yeah.
and this one also should land in X, Z.
You are very right. Oops. Yeah. Okay, these are small typos, but I hope, yeah, thank you for pointing out. Then no one is confused. No, thank you. Okay, yeah. Okay, so in general, just to be complete, we have topological spaces, big X of X0 to Xn. We think of the points in these spaces as n-dimensional directed tetrahedra, or n-dimensional, with vertices labeled accordingly. And then we have the face maps. So like they delete a vertex and give us a face opposite to it. Then we have the maps S, like they are related to the identities. So now we are not going to focus on them too much. They produce the degenerate tetrahedra. And then these maps are subject to what are called the simplicial relations that really make them behave, or like they nail in the head that they behave like taking faces. So taking a face of a face in this order should be the same as taking a face of a face in the other order, that kind of stuff. And now just a bit of like notation, let's say. So a face map is going to be called inner if we are like taking away one of the inner vertices, and it's called outer if we are deleting either the first or the last vertex. So just to establish that. Okay. An example so that you now can think of what lines and triangles and stuff is. So we start with a topological category C, like the sort of object that I defined in the beginning. The object set of this category is O. And I'm going to start defining one such functor like this that's called NC. Okay, so NC of X should be some space of points labeled X. So in this context, we only have one thing that's called X, is the object X in the category C. So we say that NC of X is the one-point topological space. Then NC(xy) should be some space of lines that go from X to Y. What is our natural candidate? Well, it's precisely the space of arrows that go from X to Y. So, okay. Next, we need a space of triangles. Well, what do we have available? We have available a topological category, so we consider commutative triangles in this category. But notice that the bottom edge is always defined by these two. It's always given by the composition. So in reality, this space is just the space of composable pairs of arrows. And then we can use this to generalize, and the space NC of X0, X1, blah, 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 is just this space of composable arrows going through the right vertices. So these do not look a priori like triangles, they are just pairs, but we know how to make them triangles and tetrahedra and so on by using the composition and the associativity, etc. So, okay, what are the maps in this case? Well, the map D1 gives us the beginning point of an arrow. That's just the source, the domain of that arrow. Similarly, D0 gives us the target. Now, what should a degenerate line be? Well, the degenerate line at X, it's the identity on X. So this is what it's meant, or what can be meant by degenerates. So now we have this outer face map that deletes Z. It just gives us this first arrow. So it's sort of a projection, takes this pair FG and just gives us F. And now this inner map takes a pair FG and gives us, like, we have to complete the triangle secretly with the composition and then take the bottom edge. So D1, this inner face map, is the composition of our category, right? And then again, the map D2, it is again an inner face map. So it has to, so a point here is just this triple, like F, G, and H, that of course we know that's secretly a tetrahedra. And so what D3 does is that it composes these two. So it gives us F and H after G. And then, okay, we know that secretly the composition of the three is there. But yeah, okay, so is this making sense? Yeah, okay. Okay, so scary words, but don't worry. This assignment that we did of taking a topological category and giving us this functor is actually a fully faithful functor, but this just means it's sort of like an embedding of categories, and it's called the nerve. That's why it's the big N. But don't worry too much about this. What I want to get to is that we know we can characterize is exactly when a functor like this comes from a category. So when it is the nerve of a category. And when is that? So when these spaces are the one-point space. So for the object just with one element, the associated space is just the one-point space. And when the Segal maps are isomorphisms. So I haven't introduced the Segal maps. So I will do it now, but it's not so hard. The Segal maps give us the spine of a tetrahedra. Let me show you the pictures. It's easier. So we take an n-dimensional tetrahedra and we get the string of lines that connect adjacent vertices. So in this case, we have this triangle. We just get these lines that connect x0 to x1 and x1 to x2. In this case, we have the tetrahedra. We get the lines that go from x0 to x1, x1 to x2, x2 to x3. Whatever this higher dimensional tetrahedra would be drawn as, we would get the spine, just a sequence of lines, x0, x1, x1, x2, and so on and so on. So, yeah. Just a little side note. So these are maps into a product. So it's enough to give a map into each of the factors. And I just want to point out here that to each factor, this map is a composition of outer face maps. So I can start by taking off x0 and then x1 and then x2 and so on till I get to xi. And vice versa, I can cut xn first and then x2 and so on and so on. All right, but this is, yeah, just more relevant to the ending slides. Okay, so maybe I should go back. We want to show that X is a nerve of a category if and only if it obeys these two conditions. So one side is easy. We have the definition of the nerve. We just have to check that these apply. So that's what we're going to do. So yeah, NC of X is just a one-point space. So that one is done. And then we have to see that the Segal maps are isomorphisms. So, this didn't, okay. So NC of XYZ is given by this. Well, the NCXY are these. So we really have this isomorphism. And then here it's the same thing, like almost by definition. We have this isomorphism, and it means that the tetrahedra are completely determined by their spines. It's like what's the being an isomorph, the Segal maps being an isomorphism means. Oh, I'm going slower. Okay, the other way around. So we have such a functor. We need to define a topological category out of it. How do we do it? Okay, the object set it's O as it's always been. Now, the space of arrows from x0 to x1 will be our space of lines. That is still in line with our whole philosophy. And now we have to define the composition. And that's the fun part. Okay. So how do we define the composition? We have to take two composable arrows, like let's say F and G. And now we know that the second Segal map is an isomorphism, so it has an inverse. And that inverse, it sort of like fills this triangle, fills this spine up into a triangle. And moreover, this triangle is unique. It always exists and is unique. That's the definition of an isomorphism. And so then we say that the composition, what should it be? The map D1, so the map taking the bottom edge, basically. This is really similar to what we did when defining the nerve of the category. So again, you have a spine, you fill it into a triangle, and then you take the bottom face. That's composition. Okay, why is it associative? Well, basically because S3 is an isomorphism. That means that for each triple of arrows like this, we can uniquely get a tetrahedra that has this spine, and because this arrow in the back is unique, it must correspond to this side of the composition and this side of the composition, just like in the beginning. Is it like, is everyone on board still? Okay, perfect. So, alternative definition, a topological category is a pair O of objects and then a functor like that, such that C of X is the one-point space and such that the Segal maps are isomorphisms. So I just show you that this is a completely equivalent definition of what a topological category is. And it's this one that we are going to generalize. But first, another example. So we're talking about spaces, spaces, spaces. Now we take X, a topological space, your favorite topological space, and we remember that we can concatenate paths. And concatenating paths, it's sort of like composing. So everything is starting to feel like it should fit also into this framework. I'm going to define a functor that's called pi less or equal than infinity of x, which is a weird name, but yeah, it is what it is. And now notice that the set O, I replaced it by the set X. So now the objects, let's say, of our functor are the points in X. Okay?
Can I ask you an elementary question?
Yeah.
Maybe even stupid. So can one draw what this functor x does to arrows? Why do we need to take the opposite?
Okay. So
I mean, you so far you have only explained what it does to objects, right?
no, for example, let me go a bit further, a bit back. That's a very good question. Okay, so for example, NC, so XYZ is an object in the category delta O. XZ is another such object. And where does D1 come from? From an opposite category, an opposite arrow in the category delta that I can show very easily what it is. So we have X, let me check, yeah, XZ into X, Y, Z. So now I call it the one like under. And so what is this? This is the line that goes from X to Y, the like platonic line that goes from X to Y. And this is the platonic triangle like this. And so this map just, just takes this edge and includes it here. Similarly, we have the inclusion of the edge XY into here, that it's the map D2, which is just the inclusion like this, and so on. So, yeah.
These are all maps. These are all the maps, essentially, right? I mean, all possible inclusions. So that's why on the other side you get all possible deletions, like compositions of these.
Yeah, exactly. So you have, for example, you have, let's say X W. You can like include it in X W. Let me not Z maybe like this, and then of course you can maybe include it into a tetrahedra X W Y Z. So yeah, you just compose inclusions of faces. Then, okay, no one asked, but I tell. The degeneracies come from taking, for example, let's say a triangle. And now I want to collapse this triangle into a line. I can only do that if these points agree. So, for example, if I have Z, like if I want to collapse it like this point has to be the same as this. And so that's why the degeneracies repeat letters in this string. So like x from x to x. Is it okay?
Yeah.
So thank you for the question. In this next example, I can show you this duality a bit better if you want. Okay, so we were defining our functor pi lesser infinity of x, the fundamental infinity groupoid of x. And so, okay, this space, what should it be? Okay, it should be the space of points labeled x. We only have one candidate, like the point x. So this space is just a one-point space. Then this space should be some space of lines from x to y. Well, x and y are points in x. We know exactly what lines from x to y are. They are lines, they are paths from x to y. So maps from the topological one simplex into x that send the endpoints to the right place with a compact open topology. Well, just these should be some space of triangles. What are the triangles? Well, there are maps from the topological to simplex into X that send the vertices accordingly. And then we generalize, and the space of n-dimensional tetrahedra is the space of maps from the n-dimensional tetrahedra into X. Of course, now the maps are also really obvious. So if I have like this triangle, what does the map, for example, D1 do? It gives me this path below it, and so on. Okay, do we have a composition? What would the composition be? So it would be something like this, like in analogy to what we've just seen. But now, of course, we don't have a composition. Like this map S2 is not an isomorphism. However, I want you to notice two things. If we pick some triangle H like this, then the bottom edge, gamma, is homotopic to the concatenation of these two paths. I mean, H really is the homotopy between these two paths. So yeah, gamma is not the composition of H and of alpha and beta, but it's not far from it.
So when you say concatenation, because there is like the parameterization is not obvious, right? So you mean the basic one where you make half the interval and then the other half?
I mean, this holds for any parameterization, but yes, pick your favorite, and maybe it's best that.
I should think of that.
But yeah, you should think of that, of like going twice the speed in alpha and beta and doing one after the other. Yeah, the concatenation. Okay, so yeah, gamma is not the composition of alpha and beta, but pretty close. And also, S2 is not an isomorphism, but it is a weak homotopy equivalence. So it is like the second best thing after isomorphism when we are dealing with topological spaces. And to model precisely this sort of composition, but not really, is where Segal categories come in. So a Segal category is a pair of objects and then a functor like the ones we've been seeing, where the first condition we keep the same. We have the one-point space for C of x, but now the Segal maps are only weak homotopy equivalences. So obviously, or not obviously, but this generalizes the notion of categories, because if we in particular have an isomorphism, we have a weak homotopy equivalence. And yeah, that's it. So why are they called? Well, they're called Segal because Mr. Segal came up with them, obviously. But why are they called categories? Because precisely we have some sort of notion of composition. Two maps, which are points in the spaces xy and yz, like with a pair, they do not have decomposition, but some points are a composition. And so the points that are a composition of f and g are the points here, and they are precisely the bottom edges of the triangles that fill this spine. So yeah, they're not unique, like in the case of our category, because we don't have an isomorphism, but yeah, we can say that they are a composition. So yeah, this is the drawing. In this case, H is a composition of F and G. All right. But okay, I mean, in a category, not only we need to have a notion of composition, because S2 is a weak homotopy equivalence, this space of compositions is contractible. And so it means that composition, even though it's not unique, is unique up to homotopy. Any two compositions are connected by a path and extra stuff. Okay. And then recall that we saw that S3 was used to prove that in the nerve the composition is associative. Here we have sort of the same thing. Because S3 is a weak homotopy equivalence, we can deduce that composition is associative up to homotopy, which is a more subtle notion, but trust me, it makes sense. I can answer questions if you have. Okay. So given a Segal category, composition is not well defined, but is unique up to homotopy, and moreover, it's also associative up to homotopy. And drum rolls, that's precisely what it's meant by weakly enriched category. So it's a category because there's some notion of composition, weakly because this composition is not unique and associative, but only weakly, so up to homotopy, and enriched because we have spaces of maps between objects. The term weakly enriched categories has like fallen in disuse. The modern word is infinity category, but I know that's a bit scarier, so I was avoiding it. But yeah, the formal statement that Segal categories are weakly enriched categories was proven by Julie Bergner in 2007, as rephrased as Segal categories are models for infinity categories. So, any questions so far?
So I guess in general, you relied on this notion of homotopy in topological spaces, but you can define homotopy abstractly without referring to topology, but just like some notion of a category where like you can compare morphisms in this way. And that would be a weakly enriched category in general, or is it even more general than weakly enriched categories?
So yeah, that's when. So here before enriched, we sort of have the top, which I didn't write, but yeah, we could have a notion of categories enriched more generically, and I am going to get to that. So that's a very, very good question. Thank you.
Can I ask?
First.
So does it make any sense to sort of take this whole notion up to homotopy and then get sort of quotient by some relation and then get an honest category?
Yes. Okay, so that's great.
And there is a reason why we don't do that, I guess. I mean, we want to keep track of this.
Yeah, we want to keep track. For example, the fundamental infinity groupoids. Well, I'm not sure where I'm going with it, but okay, yeah, the fundamental infinity groupoids. It's like a refinement of the fundamental groupoid of a space. But in the fundamental groupoid, we quotient the paths by homotopy class. So a map from a point X to Y is a homotopy class of a path from X to Y. In this case, we are keeping track of the homotopies and then of the higher homotopies and the higher homotopies. So this is sort of a refinement of the fundamental infinity group, of the fundamental groupoids. But okay, to answer your question more concretely, so suppose you have X Segal category. Yeah. So X is a functor from, delta O up into top. And the quotient you are talking about, I suppose that it is passing to the homotopy category of topological spaces, maybe?
Maybe,
It can be. So this is sort of, yeah, this is a quotient, like sort of a projection. And okay, what happens here? So we have X a Segal category. So the Segal maps are weak equivalences. When we pass to the homotopy category of topological spaces, this becomes an isomorphism. And so now this functor, because now we have an isomorphism, we can say that it's the nerve of a category enriched in homotopy types, which are the objects in the homotopy category of topological spaces. So like by passing to the quotient, we strictify basically our enrichment. But I didn't want to go into this precisely because I didn't define what enriched in H top would be, but I mean, it's fairly deducible.
But do you also get a category, so a category enriched in sets? So
Yes, you take pi zero, you take connected components.
Okay, you take the zero of the...
Well, you can take it from here to set pi zero, or you can take it from here. It's obviously factors. And so, yeah, if you have X a Segal category, you can get, so this is X, this is connected components to sets. And so again, this weak equivalence, by definition, if we put a pi zero here, we'll go to an isomorphism and we get a strictly enriched. So actually, if X is a fundamental infinity groupoid, this thing is a fundamental groupoid. We're taking connected components of the path space, is taking homotopy classes of paths.
So it's pi one. In that case.
No.
No, it's just not notationally.
Yeah, you take pi zero of the path spaces, so are related to pi one. Yeah. Yes. Okay. Where are we going? We've seen this. Okay, so a little bit of history and some applications. Why do we care, or why have people cared about this? So they were introduced in the one object case. So Segal categories with one object were defined in 1974 by Segal, and he was studying loop spaces. So in the 60s and 70s, it was like very trendy to ask, okay, I give you a topological space, tell me if it's the loop space of another space. And so, yeah, Segal used Segal categories to study this question, which is basically, so what he used was basically the fundamental infinity groupoid, but restricted to just one object, X. And so, for example, you see pi less or equal than infinity of X from XX. It's precisely the loop space of big X at X. It's the space of paths from X to X, and then the rest. They were introduced in full generality by Dwyer, Kahn, and Smith a few years later when they were studying the following question. So suppose I give you a homotopy commutative diagram, so a diagram of shape V valued in the homotopy category of topological spaces. When is it the case that we can lift it to an honest commutative diagram of topological spaces? And also related, when can it be lifted to homotopy coherent diagrams, where not only where we know that it commutes in this category, but we know exactly with which homotopies it commutes. So if you don't understand that, that's fine. Then finally, in 2001 and 2005, respectively, Simpson and Ershwitz, Antoine and Vezzosi, there's missing a dot here. Yeah, they were used to develop theory of higher stacks in algebraic geometry. So stacks, but looser and weaker and homotopical. Okay. So I told you that Bergner showed that Segal categories are models for infinity categories. If you've heard about infinity categories, the thing you've heard probably is that there's like a whole zoo of models, and some people use this model and some people use other models. Quasi-categories, simplicial categories, complete Segal spaces, theta spaces, like these are all infinity categories, and it's a bit messy. Why should we choose Segal categories? First, because the space of arrows from X to Y is very easily available. It's like you have to give it, actually, it's part of the data. And this is not the case, for example, with quasi-categories. In quasi-categories, these spaces are very hard to compute. Then there is a very well understood comparison with strictly enriched categories, so topological categories, which is the nerve that I showed you. And this is very cool because, as Nicholas was hinting, if we use other enrichment here, maybe we can use the nerve to study what the enriched Segal version should be. And then this one is just really for people who love infinity categories. They allow for inductive definitions of Segal N categories, which are models for infinity N categories. If you don't understand it, that's super fine. If you want me to answer questions about it, I can also do it at the end. Oh. Okay, so I defined to you chain-enriched categories. Nicholas pointed out precisely that other contexts also have a notion of up to homotopy, or in this case, also of weak equivalences. In the category of chain complexes, we have the quasi-isomorphisms, the second best things after isomorphisms. And so can we define weakly chain-enriched categories? Well, what would these look like? That's the question. So instead of a composition, we would have like this span. We would require S2, the second Segal map, to be a quasi-isomorphism instead of a weak homotopy equivalence, whatever. But now you have a problem. This is a tensor product, is not a product. So the Segal map is not given by mapping into here and mapping into here. So taking the first edge of the triangle and then the second edge of the triangle. Because the tensor product, like, I don't know, to give maps into it, it's not the same as to give maps into the Cartesian product. Okay, so yeah, the Segal map is not induced by D0 and D2 into each of the coordinates. Luckily, some very nice people have thought about this before, so we asked them for help. So what do we want? We want to create an alternative where we keep the interface maps because they, well, nothing wrong with them. But now we don't need the outer face maps because we are not going to use them for the Segal map. We want to replace the Segal map entirely. Okay, so that's what my work is about. So for any generic nice symmetric monoidal model category, scary words, Symmetric monoidal means we can enrich over it. Model means that it has weak equivalences. Nice means that I want to work with them. Okay, for a set O, we consider strongly unital collax monoidal functors like this. Also scary words. What do they mean? They mean that for any n greater or equal than 0, and for any pair of objects in O, we have a space of n-dimensional tetrahedra that now we don't care about all the vertices, we just care about the first and the last one. So instead of having, for example, x, z, w, and y, like these are sort of ghostly. Yeah, this is for technical reasons. Then we have the inner face maps. So, and they allow us to keep the extreme vertices fixed, like they don't eliminate any of the, nor the first or the last vertex. Okay, the degeneracies, we also keep them. And then this is the collax monoidal part. We have things like this, which look exactly like what we want to replace the Segal maps with. So, for example, if we put 2 here, we have 1 and 1 here. So we have a triangle that goes into a tensor product of 2 edges. So it's the perfect replacement for the Segal maps. So, okay, maybe, yeah. Okay, and then we can vary the set O in a technical way also, and obtain the category of A enriched templicial objects. Then, of course, the A enriched Segal categories will be the ones where this is a weak equivalence, where the Segal map is a weak equivalence. So, my work concretely. So we have the nerve, and the nerve, we can still define it in this context. It takes strictly enriched categories. So A can be topological spaces, A can be chain complexes. So we know what this side is, and we have the comparison via the nerve with templicial objects. Now there is a left adjoint to the nerve, which it's sort of a strictification sort of thing, and on this side we have a model structure that was put on it by Muru in 2015, if I'm not mistaken. And so we want to replicate sort of what the result that Bergner obtained. So put a model structure on this side such that this becomes a weak equivalence, equivalent equivalence, I should say, and that is then translated as templicial object, A enriched objects are models for A enriched infinity categories. So yeah, what you did was with top here and there. Yeah, so that's what I'm going to try and do in the next few years. Hopefully you'll get updates. Yeah, that's it.